Dr. Ashley Karp is a propulsion engineer at JPL. There she worked predominantly on Mars missions and concepts. Her main focus is on the Mars Ascent Vehicle propulsion concepts and technology development. She is the propulsion lead for the Mars Ascent Vehicle technology demonstrator and is the PI for JPL's hybrid propulsion test facility. She has worked on Mars 2020, the low-density supersonic decelerator, as well as many system studies and technology development programs. Ashley is the vice chair of the AIAA Hybrid Rocket Propulsion Technical Committee. She received her master's and PhD in Aero and Astro from Stanford University and her bachelor's degree from UC Berkeley in astrophysics, physics, and political science. So please give a big welcome to Dr. Ashley Karp. Thank you.
All right, thank you all for being here this evening. I'm really excited to talk to you about my favorite topic in the entire world, which is the Mars Ascent Vehicle. And I just want to kind of start out with a quick disclaimer. So the MAV is ITAR controlled, so a couple things end up getting a little bit more blurred than probably a Caltech audience would like, and I apologize for that, but it's for export control reasons. And the Mars Ascent Vehicle has not actually been selected as a mission yet, so it's all conceptual at this point. So this is a quick agenda. I'm going to go through an introduction, some of the history of how we ended up at a hybrid Mars Ascent Vehicle tech demonstrator, the design, what we're looking at right now, the technology development effort that we're going through, the challenges that we're having, some future work, and then I finally wrap it up with a summary, and then I'll take questions at the end. So to give some context to why we care about a Mars Ascent Vehicle and why this is interesting to us, is to put it in the Mars Sample Return, or MSR, reference architecture. So this is a multiple-step campaign that's been proposed. So the first step is to cache a rover, or to have a caching rover, and this is capability similar to what's on Mars 2020 right now, so what they're developing for 2020 to be able to cache and collect samples. Then a second mission would go with a lander, and this would have something like a MAV on it. Right now we're looking at a mobile MAV, but a pallet lander MAV hasn't been ruled out. MAV stands for Mars Ascent Vehicle. The MAV would launch the samples. So the samples would be transferred to the MAV. The MAV would launch them, and they're contained in this orbiting sample. That orbiting sample would end up in orbit around Mars through a couple of burns. And then this third mission would come and pick it up and then send it home. So it would come home either an Earth return vehicle or to near Earth and then be picked up there. So it's really a multi-step process that has a lot of really complex moving parts, and we're trying to make sure that the technology is there so that if we say, hey, I'm ready to do Mars sample return, we're not scared of having a Mars Ascent Vehicle, because right now it's kind of one of the trickier, seen as one of the trickier technologies that still needs to be worked out. So the Mars Ascent Vehicle has been studied for many years, and lots of different developments have been suggested. But most recently, in 2014, we started with a complete fresh slate. So we looked at all the past studies, what had been done, but basically started again from scratch and looked at everything we could possibly think of and then compared them with some figures of merit. So I'll just go through a couple of the different categories. We looked at a two-stage solid. It needs to be at least 2 stages because we're inserting into Mars orbit. So we need to get off the planet and then circularize. You can't restart the solid, so that's why there's a minimum of 2. We have a solid liquid, so this would get you basically to orbit with a solid, and then would more precisely insert you into orbit with a liquid upper stage. Then we looked at a monopropellant. It's lower performance, so you can see it's a much bigger rocket. Then pumped bipropellant and a regular bipropellant, regulated, so pressure regulated bipropellant. These are 2 more conventional options, so something that would require potentially a little less technology development than the hybrid. The hybrid came into study at this point too, and was kind of looking on the same size as some of the liquids. Their performance is very similar. But the nice thing about the hybrid is it can also be started multiple times. Liquid can be started multiple times, same with monopropellant. So the solids are what can only start once. Then we looked at a few multiple stage options. And we went through this, this study and our figures of merit, and really we're able to kind of wipe out most of the 2 stages except for the solid. The solid's really nice because it's a simple 2-stage solution. The other ones we crossed out for either being too long or too heavy, things like that. And the main parameters we were looking at are GLOM, gross liftoff mass, length, and allowable flight temperature. And this is what really brought the hybrid to the forefront, is this allowable flight temperature of down to minus 72 degrees C. The reason we care about that is because Mars is very cold and it cycles. So its diurnal cycle can change about 100 degrees C every day. So this is something that was going to enable us to work at lower temperatures and minimize our power requirements on the entire system. Okay, so that was our Fiscal 14 study. So Fiscal 15, oh, yeah, that's exciting. You guys will see all the rest of my charts. Jump ahead to the solution. Okay, so then in 15, we refined it a little bit more. So first we had, 10 options. We're trying to look at everything we possibly can. Now we wanted to zoom in a little bit more and add a little bit more meat to the bones, refine these potential solutions, and see where we ended up. And at the end of the year, we basically, wow, this is gonna go really, sorry, shouldn't touch that. At the end of the year, we ended up with the hybrid as the front runner. And the reason for that was really what I alluded to earlier, that the low temperature design really makes it have the most promise for the Mars Ascent Vehicle for a potential future application. So we would be able to get the lowest GLOM to start with. So the gross liftoff mass was lower than any of the other options, and I'll just flash back to that so you can see that in this particular case, we were at 219, and that's not the case anymore. But that was substantially lower than all the others, and these are all taken as apples to apples as possible. The length is a little bit long, so that's where we struggle on this design, is trying to get it as compact as possible. But the temperature requirements are really quite great. And here we were thinking that this is where the fuel could get us down to about minus 90, and it looks like so far we can probably get even a little bit lower than that. And the oxidizer, we originally had thought was minus 66, but now we're predicting down to minus 72 will be fine. Oh, yep. Taking you for a tour of my slides. Okay, so just to make sure everyone's on the same page, because a lot of people haven't heard about hybrid rockets in the past. A hybrid rocket is a hybrid between a solid and a liquid. So you have a solid fuel in almost all cases. That's shown right here. And this one in particular has a single cylindrical port. That's true for almost all the wax-based hybrids, not 100% of the time, but it will be true for the rest of my talk. And you have a liquid oxidizer. So it's a fairly simple system. It's somewhere in between the complexity of a solid and a liquid. So you have half the plumbing you would for a liquid and a little bit more control than you would for a solid. So you inject your liquid oxidizer through a control valve and break it up across an injector. You use an igniter to start a little bit of your fuel. So you basically vaporize it and the combustion occurs in the gas phase and is self-sustaining until you turn off the control valve, so it will keep going. And then this is the only equation in my entire talk, so I promise I won't get too mathy. But I just wanted to kind of point out that this is the driving equation for the design in hybrid. So this is the regression rate, how fast the fuel burns. And this is the oxidizer mass flux. So what that means is how much oxidizer per mass you're putting in divided by the cross-sectional area of this port down the center. And the reason we care about that is because this equation, when you look at it for solids, has a P in here. So this is pressure. So usually your performance is dependent on your pressure. So the higher the pressure, the better your performance. For a hybrid, it's just dependent on the oxidizer mass flux. So instead, you're just worried about how much oxidizer you're putting in, which actually gives you a big advantage because now you don't have to operate at high pressure anymore. You can operate at pretty low pressure, and that helps minimize the mass that we have to take with us. So that'll come up in a little bit later. These two are empirical constants, and that's what we're trying to derive through some of our technology development right now. So this is the baseline concept that we presented at our big final outbrief from the study for the Mars Ascent Vehicle. You'll hear me switch back and forth a little bit between Mars MAV, which I know is redundant, and Demo MAV, because we're doing a technology demonstrator. We're working towards doing a technology demonstrator in 2019. So I apologize for a little bit of redundancy there. But this is the Mars case. So we completed this design in December. It's changing a little bit still, but basically we had the team throw everything they could think of. What is the hardest thing that we can come up with in all these different areas? And so how big does that let us grow, and where do we break? Are we going to still fit into a sky crane sort of lander? And this kind of turned out to be as big as we could get. We're 346 kilograms glom, so almost 350, which as you notice is a little bit up from the 219 I pointed out in the last slide. 57 centimeter outer diameter, which is roughly 22 inches for those who think in English units, and then 2.9 meters long. So this is basically taking up as much real estate as we can give it inside of a EDL system that we've already worked for MSL in March 2020. It'll probably be a little bit more massive, the whole thing together, so it'll end up getting updated should this actually be selected. But we have the orbiting sample, so this is kind of a large basketball shaped thing with all the small individual samples inside of it here. Avionics and telecom sit below that. This is our oxidizer tank. And then the main hybrid motor is here in the middle. So it's a little bit hard to see underneath the outer fairing. There's a fairing along the outside. And then we have the helium tanks for pressurization and a bunch of propulsion components you can see along the length of the combustion chamber. We have RCS system, and then a nozzle with liquid injection thrust vector control. So this is a guided rocket. And we're doing it through a special way where basically you inject some liquid into the aft end and deflect your thrust profile, or your thrust plume. And I'll explain that a little bit further in some upcoming slides. So this was our direction because it gave us the most opportunity to grow. So it's a technology development effort for sure. This is probably the lowest TRL option. I mean, it was the lowest TRL option of all the different cases, but we could gain the most from this development. The oxidizer we're using is MON 30, so that's 70% N2O4, and often known as NTO, or but short MON, mixed oxides of nitrogen. And then SP7, which is a newly developed wax-based fuel specific for this application. And this allows us to work down to minus 72 degrees C, which really dramatically reduces the effects we put on the landed system. Okay, so there's three main areas of technology development going on right now for the hybrid. So this is our current work. This was some effort done last year at a company called Parabolas. We were doing some hot fire testing of rocket motors. This is a 10-inch motor. And we were also testing smaller motors at 3 inches. And this year we're testing more flight-like configurations in 11 inches, which is where we kind of settled out. We're also looking at all the material component capabilities. So we developed this new wax. We needed to make sure that we knew enough about it so that we could design the motor properly. So stuff like chemical analysis and pull tests for mechanical properties and all of that sort of thing. We're also doing a lot of thermal testing, so to understand, yes, this does perform over the entire range that we had predicted it would work over. We're looking at hypergolic ignition. So since I mentioned we need 2 burns, it was really important for us to be able to ignite the second time as simply as possible. And typical pyrogen igniters are basically like a solid propellant, so a lot of them require a little bit of heating. There's some ways around this, but this is a nice simple way to basically not have to deal with that, having something that we can add into the fuel where when the oxidizer comes into contact with it, it just ignites on contact. And then the thrust vector control, which I mentioned a little bit in the last slide, and I'll go into a little bit later. So liquid injection thrust vector control is something that's proven. It's been done in missiles, especially in the past. But for this particular application, it's a little bit different. So we need to understand how to make sure that it works properly. So one of the main challenges is we have this brand new propellant combination. So I went to a company and basically said, hey, we want to work in any conditions we can get on Mars. We can dial in the temperature for the actual launch, but we want to be able to survive in as wide a range as possible. And then we want really high performance, so give us the best thing that you can do. And actually, this company, Space Propulsion Group, helped us develop SP7, which is a wax-based fuel with really good low temperature capabilities. And then for the oxidizer, this is something that's been worked through at NASA and with various rockets in the past as well, are different concentrations of MON. For the Mars case, we're looking at MON 30, and that's to get us that minus 72 degrees C operation, or storage, excuse me. And for Earth-based testing, we're using MON 3 as an analog. It's more readily available, and you can test with it at room temperature, which is substantially decreasing our costs for current operations. So there's 3 companies that we are working with or have worked with to try to get this testing done and to get as much information as we can. So the first I mentioned earlier is SPG. They're the ones that developed the fuel for us. They have a lot of experience with wax-based hybrids in general. They completed some hot fire testing with nitrous oxide in 2015. And the reason for that is it's something that's relatively prevalent in the hybrid community. A lot of people know how to use it, and it's relatively safe. You can have it in the lab and not worry about it. It's not toxic. It does have some decomposition events if you mix hydrocarbons in, but in general it's fairly easy to work with, especially compared to the storables like MON. So now in 2016 they moved to MON 3, and we got a lot of really good data with MON 3. And that's going to be published this summer. So the whole regression rate curve and how this equation goes for that particular one will be published. And the comparison, the most important thing was this comparison. So we got a lot of data with nitrous, and then we moved on to the MON. And the data tracks really well. So we predicted that they had similar chemical makeups, so they should track each other pretty well. And that initial prediction allowed us to make a pretty accurate estimate for the design and have that move on through the rest of the testing. So now we've only done it up to 3 inches. This is a picture of some of the testing that they did at SPG. But we're currently working with them to build an 11-inch motor, and they'll be doing 11-inch motor testing starting as early as April. So the second company we had the pleasure of working with is called Parabolas. They did some testing at 10 inches. So this is a picture I showed earlier. But we had a few injector issues. So making sure that a stable burn was achieved was a little bit difficult, we found out, at this large scale. It took a little bit more time. And we only gave them about 6 months to work on it. So they did a great job for what we had at the time. But we still have a few issues there to work out. And then the final company is called Whitney Aerospace has a lot of experience in LGBP testing, especially with hybrids. And they're working with us this year to do an 11-inch motor as well. So we'll get a lot of test data from them starting again, probably near the end of April for Whitney. Okay, so I mentioned that one of the biggest things and why we're really interested in hybrid motors is because they have really good low temperature capability, and they should hopefully be able to survive Mars and its complicated and challenging diurnal cycles. So we did some preliminary thermal testing at Marshall. We did 201 cycles, so we did 1 EDL, then 50 winter, 100 spring fall, and then 50 summer cycles to get a look at how this would work, make sure that the samples came out unaffected, and kind of give us an idea of where to move in the future. And then we only tested 8 samples, so 4 were just neat SP7, so just the plain wax-based fuel, and then 4 we actually had aluminum additives. We were kind of considering adding aluminum or something else at the beginning, so we wanted to make sure that we had that data in case we needed it. And this will also be a good analog for some of the hypergolic additives in the future if we want to add them. So there were a couple issues with this test. So this is what the sample looks like. If all of you guys can see that down in the corner. But it's about 2.5 inches thick and then 10 inches wide. And it originally had a B to A, so the inner to outer diameter of 2 to 1. Now we've moved to 3 to 1 for packaging. We've done some testing in small scale for that, but it's something we're going to have to go back and do some more thermal testing with. And we saw a little bit of debonding, so you can't tell on this picture, but sometimes the grain would move away from the edges, but it wouldn't crack. So like a solid, we're really worried about any cracks or any debonding anywhere where you could get burning where you don't want it. For the hybrid, what we're really worried about is big axial cracks, because that can kind of speed up the burn in that direction. Small debonds here should be able to be designed around, so it should be an engineering solution as opposed to an actual catastrophic failure issue that you'd be worried on with a solid. So this is a picture of the thermal cycling that I just explained, the 201 tests, kind of compressed, so you can see the different ones, the 1 EDL, 50, then 100 of these, and then the summer. And we didn't quite hit all the targets, we were close, but we were basically able to prove at the end of this that the fuel looked reasonable to continue with, so we're really excited, and we'll be moving towards larger scales in the future. So actually more like a full-size fuel grain as opposed to the little slices that I showed you in the last picture. Okay, so ignition. So I've talked a lot about this because we want to start at least twice. So the first stage we want to do kind of pure and simple for right now. So we did a big trade study. Actually, it was carried out at Marshall. They're one of our partners on this task. And they looked at everything, every type of igniter we could think of, and did a mass trade and said, okay, we think this will be the lowest mass for this particular option. And so the lowest mass option they came back with was a hypergol. Said, okay, but no one's done that for a hybrid yet, so let's table that one. And then what's your second lowest? So the second lowest is a pretty typical pyro igniter. So you have basically a small igniter grain, and then you'd use something like a NISI to electrically actuate the first stage, then have this, will vaporize a little bit of your fuel, and you can go from there. So these are pretty standard. For the first stage, we'll fire it off the lander, which is nice because we don't even have to carry anything extra with us, so that's really convenient. But then what about for the second burn? So we'd have to carry an extra PIU, we'd have to be able to fire it. Let's try to figure out if we can actually make this better option happen. So we've been doing a lot of searching for different hypergolic additives, and for anyone who's not familiar with that definition, it just means that it ignites spontaneously when it comes into contact with whatever it's hypergolic with. And the MON is very reactive, so that's nice. It sets us up to actually have a lot of options to find. And so then we're looking at something like a design like this. We'd have our first igniter, like I explained earlier, that vaporizes a little bit of fuel, gets us going. We burn out to some point where now we're in this hypergolic layer. So we've got this layer embedded down here. So then on the second burn, your oxidizer is going to be able to directly contact this hypergolic additive, and then we'll just be able to start. We won't have to have any sort of power source to ignite the motor. We'll just have to open the oxidizer valve. So we partnered with Penn State and Purdue last year to do a bunch of different drop tests. So what these drop tests look like is basically you have a small droplet of MON, and that falls into a tube here with a little bit of additive. And it would just be a loose powder. I know it kind of looks regular here, but that's just my PowerPoint skills or lack thereof. But basically they just have a little bit of loose powder at the bottom and drop them on in, and this is what it looks like when you drop into that. So it basically combusts right away, and it will complete combustion when the MON runs out. So it'll keep going until you run out of oxidizer. When the oxidizer runs out, then it will also quench. So we've got two really good candidates that came from these two universities. And then now Purdue is looking at mixing one of these samples and some other ones. And I apologize, this is where some of the proprietary and ITAR things come in. I'm sure everyone wants to know exactly what these are, so sorry. But they're mixing one of those right now with the SP7. And the really interesting thing about this is, wax is really good at coating things. You know, people put wax on things to seal them. So the wax is acting in the same way with the hypergol. So it does a really good job of protecting the hypergol so that handling is a little bit easier, but then it makes igniting it a little bit harder. So that's why we're looking especially at this second stage and making sure that we can remove enough material so that we have access to the hypergolic particles with the MON so that it can actually come into contact properly in light. But it looks like that's been possible at this point. So this is a high percentage of additive. It's about 50%. And then now we're working our way down because something more like 20% would be more reasonable for an actual flight application. So we're looking at different ways we can basically try to increase the reactivity by making sure we have enough available exposed surface area and things like that to work with. Okay, so now the LITVC, so I promised I'd keep this talk fairly light, so I won't go too far into detail, but basically you have your combustion gases coming through the nozzle. This is my nice PowerPoint version of a nozzle here. And you inject some oxidizer upstream into the nozzle. So this is going to deflect the flow, create a shock wave, and this gives us a couple degrees of deflection in the plume. So we're only looking for 1 to 2 degrees to be able to control the MAV. So with just a couple of degrees here, we're able to get all the control we need. And then we have 4 different inlet points here. So we have 4 different injection points, and then we actually are going to plan to have 2 valves at each of these. And for those 2 valves, that'll let us basically have half the flow or double. So that's that 1 to 2 degrees that we're looking for. And one of the companies we worked with last year came up with a CFD model. So this is upside down from my image. So they're injecting up here, where we were injecting from the other side. And basically this is the same sort of thing. So you can see this deflection, and then the entire plume will actually shift about a degree or so. And they looked at a bunch of analytical data that they had in the past, different CFD models, and anchored that with a lot of nitrous oxide motors that they had tested and done LITVC testing on before. And they were actually able to find one old motor that some LITVC testing had been done on with this MON oxidizer. It was actually NTO, so no NO in it, and anchor the data with that. And it kind of turned out that there was a little bit of a discrepancy between the two. So right now we're taking kind of the happy medium between the CFD analytical result and the analytical result, and going with an estimate from the middle. And what this estimate is giving us is how much oxidizer we need to carry to be able to inject to get the control that we need for the flight, for the entire flight. Okay, so what are some of the challenges that we've been looking at? So I mentioned earlier that we have a low TRL propulsion system. So this is a brand new developed wax specifically for this application. We're looking at it with a space storable oxidizer, which is something that has been tested in the past plenty of times, but with other things. So it's a new fuel and oxidizer combination. It's something that we really have to do a lot of testing on, and that's why we've been working with the different subcontractors to make sure that we get a lot of data and fill out that regression rate equation. The multiple ignitions we just talked about, so making sure that we have the capability to be able to have our second ignition in space and inject into orbit properly. Potentially we could do even more ignitions if that works out. We could do as many as we want. It's just shutting on or off the valve. Optimal packaging and configuration. So this is really a driver for the MAV, where it isn't maybe for some other things. So we're really stuck in a compact configuration because we're inside of an aeroshell. So since we actually have to land first, we need to make sure, I don't know how I did that. Since we need to land first, we need to make sure that we can fit within the configuration that we have. And since the trade's still open and we don't know if it's going to be on a pallet lander or on a rover, we take the more constraining option. So right now we're saying, okay, we need to fit into a rover. The rover needs mobility. They need to be able to go collect the cache samples, that sort of thing. That's our worst case scenario, and that's where we're working to. Then just ignition and restart. So sometimes this is just a challenge for hybrids to make sure that you can ignite once you're at a larger port area. And then nozzle survivability, TVC, and erosion. So you're injecting an oxidizer into your nozzle, and usually the oxidizer can have some detrimental effects on your nozzle. So if you're ever looking at nozzle design, you always want to limit how much oxidizer makes it that far. So we're basically introducing it there. So we need to make sure that we're really careful about that, and we understand exactly what the effects are going to be on that particular bit of the design. And it's something we'll be doing testing with LITVC this summer. But research is being carried out in all of these areas to mitigate these challenges, and we think it's a really good option. The one other thing that I kind of mentioned in passing, and I don't know if you guys caught a whole lot, was we're talking about MON 3 for Earth-based testing instead of MON 30. And it is different. So instead of having 3% NO, it's 30% NO. So it completely shifts a lot of the thermal capabilities of the oxidizer for sure. But this is really enabling us to be able to do the testing in ambient conditions on Earth. Also, MON 3 is commercially available, so I can call up the Defense Logistics Agency and say, hey, I need some MON 3. They say, no problem, we'll be there in a couple of weeks. If I want MON 30, I have to custom make it. So I have to go find a chemist who can introduce NO into the MON 3 that I have to get and kind of work from there. So you can imagine that the cost goes up substantially for something like that. And then finally, if we test with MON 3, we get all this really good data. We've seen that from nitrous oxide to MON 3, there was a pretty good correlation. So we're hypothesizing that from MON 3 to MON 30, there should also be a pretty good correlation. So we should be able to basically track this data and have it at a much lower cost. And then say that in a few years from now, when we've got all this great data, the decision finally gets made, yes, we're actually going to do a Mars Ascent Vehicle, and oh, by the way, let's put it on a rover with an RTG. Okay, now we've got an RTG. MON 3 can be our oxidizer right away. We don't have to do any more testing, and we'll be ready to go. Since trades are still open and no selection's been made for a Mars Ascent Vehicle or Mars sample return in general, we still have to keep it open for solar panels and different options that won't have that waste heat that would be able to keep us warm. So we're looking a little bit, we're looking a little bit harder at the different options. So there is a little bit of different performance. So the ISP, the specific impulse, is higher with MON 30. So it's something that's definitely desired to be able to have that increased performance, and that's because the NO is quite reactive. And then it basically just touches everything we're doing just a little bit. So I have all the big parameters that you have for rocket design here on the left. So GLOM, I said earlier, is gross liftoff mass. Okay, we're a little bit heavier, but we're still pretty close. So then what are the kind of big hitters? We see this average OF ratio, the oxidizer to fuel ratio. And that's something that's actually a bit important during testing. So we need to know how much oxidizer to introduce to how much fuel we're going to be able to burn. So it's something we're going to be getting data that's at a little bit slightly different point. But you can see that all of these are very close. So the highest is about 5% different. So we're going to get very good data to be able to transfer that forward to be able to use for future flight. But we still have our work cut out for us. We have a lot of work to go. So we're still working on completely characterizing the new fuel. So hot fire testing with the SP7 and the MON, determining the material properties and the best way to process the fuel. So it's a new fuel. We've been kind of still learning how to make the fuel grains in the best way possible. And then further thermal cycling. So like I mentioned, there were a couple open issues with the first ones that we came up with. Then we're looking at a complete study of the CTE mismatch. So that's why I was saying that before. We're having some expansion and compression over the thermal cycling on the fuel grains. So making sure that we actually understand what's going on there, and if we need to provide some internal layer or something to be able to make sure that we can accommodate that during actual flight. The ignition testing, as I mentioned earlier, it's one of the most fun things to watch because as it drops, it just catches. And we're getting a lot of really good results. They're starting to test multiple different things at Purdue with the SP7 mixed with the hypergolic additives. And we're actually going to move to 2-inch motor testing. So it'll be small motors with the hypergol in there to see if it will actually ignite on contact. And understand what we need to do to make sure that happens, how we need to make sure that the grain is exposed, what happens if we do the first burn with a pyrogen like we're used to, then make sure that the grain will be exposed enough that we'll be able to have that second reaction just as we like it. And then nozzle and TVC testing. Okay, so this is one of the things I'm really excited about. So it's a proposed demo launch, so it's not official, but we're working towards and ordering components already for a 2019 launch of an Earth-based Mars tech demo, and this would be from a balloon. So these are kind of the steps that we've been taking, and I think you've heard me explain a lot of this through the talk so far. So we actually did this hybrid selection in Fiscal 16, so that was the down select at the beginning. Some MON testing and capability and regression rate data, so it's like the very preliminary stuff. This year we're looking at the full-scale MAV motor testing. We're going to be testing LITVC and then completing the Earth-based demo design. So by the end of this fiscal year, we should have a design complete for this. There's several subcontractors that'll be able to submit for that, and then we'll down select and start building it hopefully in 2018. We'll test the demo motor, make sure everything works properly, and then in 2019 we'll actually launch. And so we just selected a balloon launch to have the most relevant parameters for Mars. So we're trying to match as much as we can. So we'll take a balloon up to altitude and then launch from altitude and do actually 2 burns at that time. So I'm really excited about that. Okay, so just to summarize, and then hopefully I have plenty of time for questions. We've come up with this new wax-based fuel in Mon 30 Mars MAV application, and it's capable of meeting all the requirements that we have at this point. Substantial technology development is going into this. This is not just a little bit of work, it's a lot of effort from a lot of different people, a lot of different subcontractors and universities have been involved. And we're also working with a whole bunch of different NASA centers, Langley and Marshall in particular, fairly often. And then we're doing full-scale testing this year that should raise us from TRL-3 to TRL-4. And then by the time we do the launch in 2019, we're hoping to be at TRL-6, so that'll be our relevant environment. And basically the goal is to get this to the point that it could be folded into an actual Mars sample return, should that be selected in the future. So the major accomplishments we've completed this year: we got 8 successful tests on this 3-inch motor, so we got a lot of really good data. We found that tracked the previous data we'd done with nitrous oxide really well, and now we're going to be moving that into larger scale. We found different hypergolic additives, so we have at least 2 options right now that should be pretty good for moving forward to actually mix that into the fuel grain and understand how that works at the 2-inch scale, and then scale up to that in the future. This is it also mixed in, so we found something that actually works when it's mixed into the wax, which is a really good inhibitor, as I mentioned earlier. And then finally, liquid injection thrust vector control. So we've got a good idea of what our equation is looking like to give us sizing constraints on the LITVC and make sure that we can control the MAV properly. So with that, I think I've got about 15 or 20 minutes to take a few questions. I'm hoping that there will be plenty.